Okay, so we're gonna do section 4.3 today, which is about how the derivative affect the shape of a graph. Okay, just summarize what I'm gonna do today. I'm gonna go over, in the previous section we defined what a critical value is, a critical number is, which is a value where the first derivative is 0 or undefined as long as the function is defined at that point. Okay, beginning of the derivative, I said using the derivative we're going to be able to find those values, points of relative max and relative min, using calculus, something we couldn't do in college algebra. We're also going to determine concavity of the graph. When is it that the graph is concave down, on which interval? And then when is it concave up? And when does it switch concavity? That's in the second derivative. So we will use the first derivative to determine increasing, decreasing points of maximum and minimum. We'll use the second derivative to find point of inflection, concavity down and up. That's basically what this section is all about. Very important results of the derivative in terms of the shape of the graph. To do so, we're going to discuss first definition of increasing and decreasing, and there's a handout. I don't want to write this down, there's a lot of writing. There's a handout on like the third page after 4.3. It says definition of increasing and decreasing. A function of f is increasing on an interval if as x1 is less than x2, f of x1 is less than f of x2. So like for instance, a function is increasing on this interval from x1 x2, because when x1 is less than x2, f of x1 is actually less than f of x2. Okay, so as x increases, so does y. That's what this means. So you can see the graph is rising on that interval, and it would be decreasing, like here it's decreasing from 0 to infinity. Why? Because if you pick any x1, x2, where x1 is less than x2, then the y values behave the opposite way. F of x1 is actually greater than, so as you move to the right, your y values get smaller. Here, as you move to the right, your y values get bigger. Okay, and these are the definitions, so make sure you read them. So now the next result is a theorem about derivative and decreasing functions. Let f be differentiable on an interval, then if the first derivative is negative, then the function is decreasing. If the first derivative is positive, then the function is increasing. That's very important. You can see from, let's say this is point A and this is point B. So you can see this graph is increasing from negative infinity to a. Why? Because the slope, the first derivative, is positive. The slope of the tangent line is positive. Here we have a zero slope. Then it changes from positive to negative. So the first derivative is negative on that interval. So we have a decreasing function. Then it's zero first derivative and then positive, which means increasing. Okay, so that's what this is about. As long as the function is differentiable on the interval. If the first derivative is negative, the function is decreasing. If the first derivative is positive, is decreasing. And if 0, then we have a constant. Then f is a constant. At 0, that's the first derivative 0. Okay, it's a horizontal line. So what are the guidelines for finding intervals on which f is increasing or decreasing? This one, it's in the notes. It's not a handout, so I'm going to write it down for you. Guidelines for finding intervals on which a function f is increasing or decreasing. So if the question says, they give us a function and they say determine the intervals on which the function is increasing or decreasing, this is what you do. The first thing you do is find the critical values of f. What do a critical value mean? To find the critical values, you find the first derivative, you set it equal 0 or undefined. Okay, as long as those critical values, f is defined at those values. Okay, and then use those critical values to determine test intervals. Use critical values to determine test intervals on the number line. On the number line. So basically you're gonna do, so say you got a couple of critical values, 0, so C1 is negative, C2 is positive, you do that, and then you do your intervals, negative infinity to C1, C1 to C2, C2 to infinity, depending on how many critical values you get. And then you use this result. If the first derivative is negative, then the function is decreasing. So you determine the sign of the first derivative, determine the sign of f prime. Where do you get f prime? You already found f prime right here. You found f. You plug a test value from each interval. You pick a test value and you plug it in the equation of f prime. If f prime is positive, then the function is increasing. So you determine the sign of f prime. You determine the sign of f prime at one test value from within each interval. And then you use the result that we talked about to make your conclusion. If the first derivative at that test value is negative, the function is increasing. If f prime is negative, f is decreasing. F prime is positive, f is increasing. And that's how you determine that. Okay, so now you're going to look at an example about this. So we have f of x equals x minus 2 over x plus 3. We're going to determine the intervals on which this is increasing or decreasing. So we're going to find the first derivative first using the quotient rule. So we take the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1 over the bottom square. So f prime of x equals x plus 3 minus x plus 2, so it's 5 over x plus 3 squared. So to find the critical values, we say f prime equals 0 or undefined. 0 is never, because 5 is never 0, so that fraction will never be 0. F prime is undefined when x is negative 3, but negative 3 is not, again, is not a critical value, because when we plug it in there, it gives you undefined. Remember, it has to be plugged in there to get the y value, which we can't do that. So no critical values. No critical values. So what we're going to do, since we don't have a critical value, we're going to do the intervals from negative infinity to negative 3, negative 3 to infinity, although it's undefined. We just plug the undefined one since we have no critical values. So we find a test value within each interval. That's like negative 4 and then 0. We plug it in the equation of f prime right there. So that's negative 1, 1, 5 over 1 is positive. We plug a 0, it's positive. So the function is increasing from negative infinity to 3 and increasing also from negative 3 to infinity. So f is increasing on negative infinity, negative 3, and you're negative 3. So we cannot say negative infinity to infinity because it's undefined there. That's why we have to make two intervals here. Okay. So now what we call first derivative test. What is the first derivative test? This will tell us if a value is a relative max or relative the first derivative test. Since we're calling it the first derivative test, there must be a second derivative test. We'll talk about this later. The first derivative test for finding relative extrema. And remember, this is for relative or local, but not for global, okay? Relative extrema. So basically, before I write down the steps here. I mean, they are in the notes. I'm not going to write them down, okay? So basically, this is what you're gonna do. You can see what happens before a relative max and relative min. This is a relative max, and this is a relative min. So you can do before a relative max, the function, so C1, C2, C1 f of C1, C2 f of C2. Before C1, the function is what? Is increasing because the first derivative is positive, and then at C1 prime is 0, and then the function is decreasing. So if the function changes sign from increasing to decreasing around C1, then C1 f of C1 is a point of maximum, meaning if first derivative is positive before C1 and negative after C1, then at C1 we have a relative max right here. If f prime is positive over the interval between x and between a and c, which is before c, and negative after c, between c and b, then f has a relative max at c. And if the first derivative is negative before c and positive after c, then it must be 0 at c2. That's what before. And if the first derivative is positive or negative on both sides of c, like for instance, if you have something like this, like x cubed, you have positive first derivative before 0, and then positive for the first derivative after 0. So at 0 you have no max, no minimum. If the first derivative is positive or negative on both sides, then f has no relative extrema at c. So this is called the first derivative test for relative extrema. In order to use it, you have to first find what? The critical values of f. And how do we find a critical value? We find the first derivative, set it equal to 0, or the first derivative is undefined as long as the function is defined at critical values. Keep that in mind. Okay, so example. So use the first derivative test to find all relative extrema. There's always a standard question on the test about that, okay? Of the function f of x equals x to the 4 minus 32x. So the first step is to find what we call critical values. And to find those critical values, we find the first derivative. So that's going to be 4x cubed minus 32. So we say a critical value is a value where the first derivative is 0 or the first derivative is undefined. So 4x cubed minus 32 equals 0. This is undefined, never, because it's a polynomial function. So 4x cubed equals 32, x cubed equals 8. So the only real critical value here is 2. There's 2 imaginary ones that we have no use for. So that's the only critical value. So how do we test if it's a point of maximum and minimum? We use it to divide the number line into intervals. Negative infinity to 2 infinity. We find a test value. So between negative infinity and 2, I'll pick the easiest one, is 0. Between 2 and infinity, I plug it into the equation of the first derivative because based on the sign, I don't really care about the value. It's just the sign of f prime. So we plug 0 in there, you get negative. I don't really care about the value, just the sign. If you plug 3, 27 times 4 is much bigger than 32, so it's a plus. If the first derivative is negative on an interval, then the function is decreasing on that interval. If the first derivative is positive on an interval, then the function is increasing. So you know we have, just like it looks like, we have a relative at 2. We gotta find the y value. Actually, it's a global min because the graph is gonna look like this. Where do we plug the 2 in to get the y value? All the way back into the original equation. We have a calculator and we use it, so we get this value. So 2 negative 4 is a relative, and it's also a global minimum because you can see what the graph is gonna look like. Here's another example. Again, find all relative extrema of this function, f of x equals x to the third minus 4. So we find the critical values by finding f prime of x. It's 2/3 x to the 2/3 minus 1. So it's 2/3 cube root of x. So we say f prime equals 0 or f prime is undefined. It's not 0 because the numerator, so never 0. It's undefined when x equals 0, right? When x equals 0, 2/0, which is undefined. Now the question is, can we plug 0 into the original equation and get a y value? Yes, we can, because f of 0 is 0 to the 2/3 minus 4. So actually it has a y value. So 0 is the only critical value. Is the only critical value of f, which means 0 is the only candidate for relative max or relative min. How do we go from candidate to a sure one? We gotta do the first derivative test. And the first derivative test says divide your interval, your number line, using the critical value. Pick a test value. The easiest one is -1 and 1. Sine of f prime. So we plug that into f prime right there. The cube root of -1 is -1 times 2/3, so it's -2/3. The cube root of 1 times 2/3 is 1, so it's positive. So the function is decreasing, increasing, although the function has no derivative at 0. 0 is a critical value and 0 is a relative, which is also a global min, and the y value is -4. I'm gonna show you the graph so you can see what's going on. So if we graph y equals x to the power 2/3 minus 4, and you can see how the graph is decreasing to 0, -4, and then increasing, and you can see how we have a sharp edge at 0, -4, which means it's not differentiable, but 0, -4, not only it's a point of local minimum, it's also a global minimum. It's absolutely the lowest point on the graph. Okay. Example 3. Trying to show you a variety of examples. F of x equals x times ln of x. Again, remember this has a domain. I'm writing the domain because it's not something all real numbers. It's just 0 to infinity. Okay. So to find the critical values, we find the first derivative using the product rule. So x times derivative of ln of x, 1/x. ln of x times derivative of x is 1, so it's 1 plus ln of x. So f prime equals 0 or undefined. F prime equals 0 when 1 plus ln of x equals 0. ln of x equals -1, e to the ln of x, e to the -1. So that's one critical value. It's undefined on the interval 0 to infinity, which is the same as the domain. So no critical values there, because anything we pick here, it has to be, it has to be in, you have to be able to get a value there. Okay. So now we use 1/e to divide. It's about 1/3, -infinity to 1/e, and then 1/e to infinity. Test value, sine of f prime, and then f. Test value, I'll just use 0, and then I'll use 1 in there. If we plug 0 in the equation, I can't use 0, I'm sorry, -infinity to 1/e. Yeah, I can't use 0 because 0 is not in the domain, so I gotta use somewhere between 0 and 1, sorry, somewhere between 0 and 1/e. I can't use -infinity, domain is 0 to infinity, okay? So I have to use somewhere between 0 and 1/e. So if you put 1/e in your calculator, 1 divided by e it's roughly 0.36, so I'm going to use 0.25, okay? And then I can use safely, I can use 1 in there. So if I 1 plus ln of 0.25, all I care about is positive or negative. It's negative. If I do ln of 1 is 0 plus 1, so it's positive, decreasing, increasing. So we have a local minimum and also a global minimum at 1 over e, and the value, if you put it in there, that's negative 1 times 1 over e, negative 1 over e. Okay. Now the next one on page 18 is for you, page 18 in the notes. That's for you to work on. It's worked out, but I want you to work it out, okay? So you can practice that. And there's a couple more examples on page 19, on the top of page 19. Also work them out. And if you're not sure about the answers, you can shoot me an email and I'll help you out with those. Okay, so we use first derivative along with increasing, decreasing. You know, if the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. And then with that, if the function changes from increasing to decreasing around c, then it's at c we have a relative max. If the function changes from decreasing to increasing around c, then that's a point of relative min. So that's the first derivative. Now what does the second derivative say about f? Okay, what does the second derivative say about the original function f? Okay, so to do so, we're going to talk about concavity, the definition of concavity. So let f be differentiable on an open interval I if the graph of f lies above all of its tangent lines on I, then f is concave up on I. If the graph of f, this is the graph of f, lies above its tangent lines, you can see any tangent line you draw on the interval from 0 to infinity in this case, f is always, the graph of f is always above its tangent lines. Then we say the function f is concave up. Can we talk about concave up here from negative to infinity? No, because the function is not differentiable at 0. Remember, it has to be differentiable on that interval. So no concavity for the absolute value of x because no differentiability at 0. It would be concave down if the function, if the graph of the function lies below its tangent lines. Okay, if it lies below its tangent lines. Again, that's in the notes. Now the test for concavity, it's very easy. Actually, I have it out for that. Yeah. Okay, and then how to find the actual x coordinates of the points of inflection. Well, so you can determine where a function is concave up and where it's concave down by analyzing the sign of the second derivative. Okay, you find the second derivative and then set it equal 0, or where it's undefined. It's like finding the critical values, but in terms of the second derivative. So what are these values called? There's no specific name for that. You find the values where the second derivative is 0 is undefined. Draw a number again, just like before. Choose a test value and then you determine the sign of the second derivative, right? We used to determine of f prime, now f double prime. If the second derivative is positive, the function is concave up. If the first, so positive is up, like it says, and second derivative is negative, the function is concave down in that interval. Okay, that's for concavity. And here's an example. So find the intervals on which f is concave up and down. F of x equals negative 3x to the fifth plus 40x cubed plus 135x over 270. Now before I use the quotient rule here, I want to simplify that because I gotta find two derivatives. So I'm gonna split it up. Negative 3 over 270x to the fifth plus 40 over 270x cubed plus 135 over 270. Reduce first, always do algebra and trig before calculus. So that's negative 1 over 18, sorry, negative 1 over 90 x to the fifth plus 4 over 27x cubed, and that's 1 over 2x. So now we find the first and second derivative, negative 5 over 90 or negative 1 over 18 x to the 4. That's 4 over 9x squared plus 1/2. If we were doing the critical values, we stop there, but since we're doing concavity, we're going to do the second derivative, negative 4 over 18, which is negative 2 over 9 plus 8 over 9x plus 0. So you find the second derivative and then you set it equals 0 or undefined. So f double prime is 0 or undefined. It's not undefined because it's a polynomial. Negative 2 over 9x cubed plus 8 over 9x equals 0 times by 9 to get rid of the fraction. Negative 2x cubed plus 8x equals 0. Factor out negative 2x. So it's negative 2x, x squared minus 4 equals 0. So x equals 0. And we have 3 points that are values that we could use to determine concavity. So we're going to do, since the domain is all real numbers, we're going to do negative infinity to negative 2, negative 2 to 0, 0 to 2, and then 2 to infinity. And then we pick a test value from within each interval, negative 3, here negative 1, 1, and then 3. And we plug it into the second derivative. We have a calculator, use it. This is the equation we're going to plug it in. And if you plug it in, you get positive, negative, positive, negative. So if the second derivative is positive, then it's concave up, and if the second derivative is negative, then the function is concave down. Positive meaning the graph of f is concave up, down, down. So the graph is concave on negative infinity, negative 2, union 0, 2. F is concave up on negative infinity, negative 2, union 0, 2, and down on negative 2, 0, union 2 to infinity. Okay, that should be your final answer. Okay, now to points of inflection. So basically, what makes a point of inflection is when graph changes concavity from down to up or from up to down. Like around there, there's a point of inflection, and around there. But how do we find these exact points of inflection? Okay, so we're going to define that and then talk about how to find it. Definition, points of inflection, POI. If f is continuous on an interval I containing some number c, if the graph of f changes, if the graph of f has tangent line, so you have to have differentiability there, tangent line at CF of C, then CF of C is a point of inflection of the graph of f if the graph changes concavity around that point. So you can see how the graph changes concavity from down to up. So this must be a point of inflection. Then from up to down, this must be a point of inflection. Okay, that's what makes a point. And the graph has to be, you have to be able to draw a tangent line at that point. Okay, otherwise it won't be a point of inflection. So as a remark, if we have a point of inflection at CF of C of f, of the graph of f, then we know that either the second derivative at C equals 0 or it's undefined at C. Just like critical point of relative extrema. Now, is the converse true? If the second derivative equals 0, does that mean we have a point of inflection? Of course not. Okay, you look at x cubed. No, not x cubed, because it does work there. Okay, you look at x squared. The second derivative at 0 is 0, but at 0 we don't have a point of inflection. Like f of x equals x squared. The first derivative is 2x. The second derivative, no, it's 2. So you no, that's not a good example. Anyway, so if the second derivative, I was looking at x to the 4. Sorry, x to the 4. Look at x to the 4. Yeah, x squared is not going to work. F prime of x is 4x cubed. F double prime at x is 12x squared. So you can see at 0 we have what? The second derivative 0, but at 0 we don't have a point of inflection for x. It's a point of minimum, but not a point of inflection. Okay? So a second derivative equals 0 does not mean we have a point of inflection. But if we have a point of inflection, either the second derivative is 0 or it's undefined. So how do we find the points of inflection? To find points of inflection, first find the second derivative was 0 or the second derivative is undefined. Okay, and then use these values to divide the number line. Use these values to divide the number line into intervals. Pick a test value and plug it in the equation of the second derivative. If f changes concavity around CF of C, then CF of C is a point of inflection. Okay. Number 10, page 301. Number 10, page 301. F of x equals 2x cubed minus 9x squared plus 12x minus 3. And they want the points of inflection. So let's find those. So the first derivative is 3 times 2 is 6x squared minus 18x plus 12. The second derivative is 12x minus 8. So okay, so we want to do critical values and we want to do the points of inflection. Okay, we want to do both. So to find the critical values, we look at the first derivative equals 0 or undefined, just so you see the difference. Okay, the first derivative equals 0. It's not undefined because it's polynomial, so divide by 6 and factor. So we get two critical values. Okay, x equal 2, x equals 1. We use these critical values to divide our number line, which is negative infinity to infinity, into negative infinity 1, 1 to 2, and 2 to infinity. We pick a test value 0, 1.5, and 3. We plug it in f prime because we're doing critical values and relative extrema. So f prime is right there. We plug it in there. At 0 we get positive, at 1.5 we get negative, and at 3 we get positive. You can check that. So the function would be increasing, decreasing, increasing. So we have a relative max at 1, and we have a relative min at 2. The y values we get by plugging them into the original equation, and we got those values. To do the point of inflection, we do second derivative equals 0 or undefined. It's not undefined because it's a polynomial, so 12x minus 18 equals 0. X equals 18 over 12 or 1.5. So we do negative infinity to 1.5, 1.5 to infinity. We plug a test value 0 and 2. We plug it into the second derivative because we're doing points of inflection. We plug it in there. That's a negative, that's a positive. The graph is concave down, up, so we have a point of inflection at 1.5, and the y value, if you plug it in, and you can check the graph for that. Okay, now I want to look at 36, page 306, number 36, page 306. That's still a long section, we're not done yet. It says, sketch the graph of a function that satisfies the given conditions. We have a vertical asymptote, x equals 0, which is the y-axis, and then f prime of x is positive if x is less than negative 2. F prime of x is negative if x is greater than negative 2. X is not 0. We know x is not 0, it's a vertical asymptote. The second derivative is negative if x is less than 0, and the second derivative is positive if x is greater than 0. Let's piece that together to get a decent graph. So x equals 0 is a vertical asymptote, so that's axis, we can't mess with that. X equals 0. Now at negative 2, before negative 2 the function is increasing, the first derivative is positive. We don't know how high up it's gonna go. Okay, it could be this, it could be that, and then after negative 2 it's negative, so the function is decreasing. We assume it's gonna go along the vertical asymptote because that's what they made it look like. The second derivative is negative if x is less than 0. You can see that if x is less than 0 the function is concave down, and the second derivative is what? Is positive if x is greater than 0, so it's concave up when x is greater than 0. So you can see decreasing and then decreasing again. Okay. Number 58, page 307. F of x equals x minus sine x, where x is between 0 and 4 pi. And it says find intervals of increase, decrease, local max, local minimum, concavity, everything. Okay, so they want everything basically. So let's start with the first derivative. Its derivative of x is 1, derivative of sine is cosine. So to do critical values, f prime equals 0 or undefined. It's not undefined, it's a cosine, so 1 minus cosine x equals 0, cosine x. And if we're looking at this, look when cosine is 1, it's at 0, and then at 2 pi, and then at 4 pi. That's it, we can't go beyond that. So we're going to do, and the interval that we're looking at is 0 to 4 pi, so we're going to do 0 to 2 pi, and then 2 pi to 4 pi. That's all we can do because that's the domain. A test value, we can pick pi or pi over 2, we can pick 3 pi or anything else. Prime is positive if you plug it in there, and if you plug it in there it's positive also, because that's negative times negative is positive, so the function is increasing, so no relative extrema. Now to determine concavity, so you can see the function is increasing from 0 to 2 pi and then increasing again from 2 pi to 4 pi, but no relative extrema. To find the second derivative, it's going to be derivative of 1 minus cosine. Derivative of 1 is 0, cosine is negative sign, so it's x. So the second derivative is 0 or undefined, but it's never undefined, it's a sine curve, so sine x equals 0. It's at 0, at pi, at 2 pi, at 3 pi, and then at 4 pi. So we divide that into intervals, pi to 2 pi, 2 pi to 3 pi, and then 3 pi to 4 pi. We pick a test value, pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. We plug this into the second derivative, which is sine x. So we get positive, negative, positive, negative. So if the second derivative is positive on the interval, that's concave up, down, down. So we have a point of inflection, a point of inflection. So 3 points of inflection at pi, pi. How do we get the y value? We plug pi into the original equation. 2 pi, 2 pi, and 3 pi, 3 pi. Okay, so that tells us how to find all what we talked about we're going to find. Now, what I'm going to do next is called the second derivative test. Really, you can live without that. You don't really need that. The only thing is, it's sometimes easier to test for relative extrema using the second derivative test for relative extrema. Remember, we use the second derivative, and I want to stress that. Use the second derivative to determine concavity. We never said we can use the second derivative to determine relative extrema. We use the first derivative to determine relative. So this is an extra test. It's called second derivative test. It uses the second derivative test to determine relative extrema. Yeah, weird. It doesn't always work, but sometimes it's easier than the first derivative. It's less work. But you can live without this. You really don't need that, okay? You really do not need that. So suppose f double prime is continuous. So not only it's differentiable twice, its second derivative is continuous on an interval containing C. Containing C. Part A, if the first derivative at C equals 0 and the second derivative at C is positive, then f has a local min or relative min at C f of C. Okay, usually we find the first derivative to get the critical value, and we do the test, the first derivative test, increasing, decreasing, or decreasing, increasing. Now, you find the critical value, and then you plug it into the second derivative. Okay, that's weird, I know, but that's if the second derivative at that critical value is positive, then the function is concave up, right? Which means we have a local minimum at CF of C. Okay, if f prime of C is 0 and you plug C in the second derivative and you get negative, meaning it's concave down, meaning f has a local or relative max at CF of C. And if f prime at C equals 0 and you plug in the second derivative and you get 0, then test is inconclusive. That's why it doesn't always work. Inconclusive. What do? We use the first derivative test in this case. Okay? Use the first derivative test. And part D, if f prime at C equals 0 and the second derivative at C does not exist, then again test is inconclusive and use first derivative test. Inconclusive and use the first derivative test. So do we have to use the second derivative test? No, but sometimes when we're doing application, as you will see in optimization problems, it might be a little bit easy to use the second derivative test. So all what you have to do to use the second derivative test is find the critical values and plug it into the second derivative. If it gives you a positive answer, it's concave up, meaning relative min. If it gives you a negative answer, it's concave down, meaning relative max. If it gives you 0 second derivative or undefined, it's inconclusive, and then you have to go back to the first derivative test. Okay, just one example and I'm done. Use the second derivative test to find all relative extrema of f of x equals negative x to the 4 plus 4x cubed plus 8x squared. So we find the first derivative, which is negative 4x cubed plus 12x squared plus 16x. And then we find the second derivative, which is negative 12x squared plus 24x 16. Now we set this equals 0. So it's going to equal 0 when negative 4x cubed plus 12x squared plus 16x equals 0. So we're finding the critical values. We pull out negative 4x, x squared minus 3x minus 4. Factor that, x minus 4, x plus 1. So the critical values are 0, 4, and negative 1. So now we take each critical value and plug it into the second derivative. 0, 4, negative 1. F double prime at 0 is positive, so we have a relative minimum because it's concave down. It's concave up, sorry. At 4, it's negative, so we have a relative max. And then at negative 1, it's negative. We have a relative max there. So what are the minimum? And at 0, the y value is 0. At 4, the y value, if we plug it in, I did the work. And then at negative 1, the y value is 3. Okay? And that gives you, and that's the longest section that I've done so far.